So today I'm going to start lecture 52, and this is essentially a review of the response surface method chapter. That's chapter 6 of my book. I'm Dr. Ranjan Ganguly. And I hope you are benefiting from this particular lecture series on optimization. If you are doing so, please remember to subscribe to my channel. So I will keep producing such videos and keep motivated on this particular task. Now at the start of the chapter we saw that response surfaces are polynomial functions which seek to model the objective function and constraints. And response surfaces are part of a larger framework which is often known as surrogate model or meta model. Meta model being a model of a model, surrogate model being a substitute of a mathematical model, typically expressed in terms of some functional representation. Now response surfaces are more specific because they typically are used in the context of polynomials. Now the primary aim of using response surfaces is to simplify the solution of optimization problems. And we saw that for many engineering problems, the objective functions and constraints are calculated from computer programs. And this is something which is not realized by many people who think that optimization works on mathematical functions. Now, many nonlinear programming books, you will see a plethora of functions or test functions being used, and that's all great. But the reality is that when you want to use the optimization methods in any industry, you have to deal with computer programs. Now, it's difficult to integrate these computer programs with the optimization algorithms, which are also typically programs themselves. And response surfaces give simple polynomial models of this functional relationship between the objective function and design variables, which is typically not known in a real-world setting, but in many books on mathematical programming, these functions are presumed to be some functions of x1, x2, x3, and so on. So essentially, at a very broad level, response surface methods decouple the analysis problem and the optimization problem. We also saw that response surfaces smooth out deep local minimum, which are not useful in the context of robustness of the design, because your design must not be too sensitive to small perturbations in the design variable. We also saw that various perturbations take place due to manufacturing problems in the world, and these manufacturing problems are not particularly good for perturbations in terms of the design variables. So again, any robustness in design which is obtained by the smoothing process of response surface will be better in terms of any real world problem. Now the most simple context in terms of design is the 2K design or the factorial design with two levels. And this is often used to create linear models of the response, and many times if you look at books on response surface methods or on quality control, you will find that 2K models are often used. So this is the broad concept of factorial model. Now one of the things we can do is add a center point and then further points to it to create more number of points which are required to develop decent quadratic response surfaces. We have also seen that the central composite design or the face-centered design are some of the best approaches if you are looking at creating quadratic response surfaces. And in fact, I would suggest that these designs are probably the best in terms of using with actual engineering optimization problems. We also saw that the best way to use response surfaces is to move through the design space using sequential response surfaces. And it's better to use response surfaces which are typically quadratic or at the most cubic while moving through this design space. And we create a kind of trust region around a certain point. We find the best value of the function at this design space or in this design space, and then we take that new point, we create a new response surface around that point, and we move in this manner throughout the design space. Now sometimes you may need to create response surfaces through higher degree polynomials, maybe cubic, quartic, and so on, and you may need a larger number of experimental points to fit the curves properly or to find the larger number of regression coefficients which you are going to get. So whenever we see the need of third degree, fourth degree, fifth degree, sixth degree, and so on type of response surfaces, which may give a better resolution of the design space, we can look at some more designs. For example, we can look at the 3K design. We can also look at the 5K design. So the 3K design would have 3 levels, that is low, medium, high. The 5K design would have 5 levels. You could even have a 7K design or a 9K design. That's up to you. Now, typical approach is actually to work with these 2K and 3K designs and to try something known as progressive lattice sampling, which is essentially develop either subscale designs or add more points. We also can use some kind of probabilistic values or random numbers to enhance the design if we suddenly find that we are in need for more points and we do not have a proper way to generate them. Randomness always works out well in many situations because you get a stochastic kind of situation. Now we saw that the typical factorial design, because it's dependent on 2 to the power of k, generates a huge number of points. And therefore, fractional factorial designs such as the OA have been suggested by many people, such as Taguchi, and they are widely used in the context of quality. But in many cases, you can fit a response surface through fewer points if you use some of these fractional factorial designs. And in our previous lecture, we have discussed some of these designs, for example, the L9, the L18. And if you go into the literature, you are going to find many more such examples of fractional factorial designs in case your problem size is very large. Recall that one of the problems of response surface method is that if the dimensionality of the problem is large, that is the number of factors or the number of design variables is more than 10 and certainly more than 15, then you encounter the so-called curse of dimensionality and your problem size becomes extremely large. Now, one more use of OA is to sample the design space sparsely. And though we have spent a lot of time on the gradient-based optimization method, we have not discussed one lacuna which is present in all these methods. That is, how do you come up with a good starting design? And in many cases, people will tell you that maybe you can have a conventional design developed using conventional design philosophies as a starting design. But if you are designing a completely new vehicle or system, for example, if you are designing a UAV, or maybe you are designing a rotorcraft which is going to fly on Mars, then you may not have a starting design coming from prior experience. In those cases, you can roughly sample the design space using a typical OA, for example, or one of the fractional factorial designs. So here you do not build a response surface. You simply calculate the function values at all the points which are given by this particular fractional factorial design, and you choose the best point. That is, you choose the lowest point in terms of the objective function and also make sure that your constraints are satisfied. So this is going to sample your design space in a rough manner, and it's going to give you a reasonably good starting design for your optimization problem. Now there may be a situation where you do not have the time to actually solve the optimization problem using any formal methods such as gradients or stochastic methods and so on. In those cases, if your supervisor is telling you you need to come up with a good design, you can use some of these fractional factorial designs to sample the design space and take the best possible point which you get and present it as an improved design. And this is certainly a legitimate way to find an improved design, because remember that all points which are in the feasible region, that is where the constraints are satisfied, are feasible design. And therefore, what you are doing in optimization is you are trying to find the best point among a plethora of points which are present in the feasible design space. And again, sampling this design space, whether you do it using one of the fractional factorial techniques, or you could do it using a factorial design itself, or you could do it in using random sampling, are all legitimate methods. So again, there are situations where such practices can help you and save you in a complex situation. So I will end this video here, and with this we end the chapter on response surface method. I hope you enjoyed this chapter. I certainly find this part of optimization very interesting, and it also tells us that optimization is more of an art than a science, at least in terms of practice and actual usage in the real world setting. Now the next chapter is going to be very interesting. It's a pretty large chapter. It's on stochastic optimization methods. So here we are going to discard all this gradient based thinking, and we are going to only rely on function value calculation, constraint value calculation, and random number generation. So we are going to study GA, we are going to study particle swarm, ant colony, and maybe a few more methods if time permits. So again, probably the next 10 to 20 lectures would involve stochastic optimization, and at the end of that we would culminate the course. Now I am trying to closely follow my book in this course, so if you feel the need for any solved examples, you can consult my book where I have actually developed response surface methods, and I have solved traditional problems using response surface methods, so that will provide you a good background on this subject. So I'll see you in my next video. Stay tuned to my channel.